Okay, so we're going to solve the table and pulley problem. If we first analyze each box and we analyze the free body diagram for each box, that'll help us kind of understand what's going on here. If we start with box A and we draw out box A has four forces acting on it. It has the force of gravity pulling it down. It has the normal force pushing up. It has tension, so Ft, because it has this cable attached to it. And resisting motion is frictional force. So that is the free body diagram for box A. If we analyze box B only has two forces acting upon it. It has Fg trying to pull it down, and in the upward direction it has Ft, tension, that is caused because of the cable that's attached to it. So those are the two free body diagrams that you would need, so you can kind of see what forces are acting and where they're acting. Now if we analyze this problem wants us to find the acceleration of the system. So the system means that there are more than one object, so you guys can, I think, see that there are two objects there. And if we think about the motion of this system, there are really two things that are going to cause this motion. First of all, we're going to have Fg acting here. So I'm going to write this over here to the side, and maybe we can separate this out. Fg is going to be pulling box B down, and up here box A has our frictional force that is going to oppose that motion. So if we look at this from a conceptual level, if Fg is greater than Ff, then this system will accelerate. If Ff is greater than Fg, this system will not accelerate. So we basically need to now go through and solve those two forces out, and we can compare them, we can see what's going to happen overall. So we'll start with box A, and we'll start by solving. I'm going to write box A up here. We're going to start by looking at what we need to solve for frictional force. So what we need to solve for frictional force is Ff equals coefficient times normal force. So here's our equation. The original problem gives us the coefficient, so we have mu. We don't have Fn, so that's a little bit of an issue. We're going to have to find Fn before we can find Ff. So if we analyze our drawing over here, we can see that box A is sitting on a horizontal table. So this matches up with diagram number 1 out of your notes, which means the relationship Fg equals Fn holds true. So in other words, we can solve for normal force if we can solve for Fg. And we can solve for Fg because the problem gives us the mass of the box. So I'm going to write the equation Fg equals ma. This is what we're going to need to solve for Fg. So I'm going to go ahead and plug numbers in here. Fg equals 5.0 kilograms times 9.8 meters per second squared. So that Fg comes out to be 49 newtons. Okay? And we know, since this is diagram 1, that Fg and Fn are the same. So Fn equals 49 newtons as well. And now we have all the information we need to solve for Ff. So I'm going to pull back down this equation, and we're going to say Ff equals our coefficient, which is given in the problem, times our normal force, which is 49. And we can figure out what our force of friction is going to be. And that's coming out to be 7.4 newtons. Okay, so we'll kind of box that in. That's going to be important here in a couple of seconds. We'll come back to that. The other force that we said that played a role in the acceleration of this system is the Fg that's acting on box B. So I'm going to label box B here. And I'm going to solve out Fg, which is a little bit easier than solving frictional force. Fg equals ma. Fg equals 2.0 kilograms times 9.8. And so Fg is going to equal, once we round this back to 2 sig figs, because that's what we're looking at here, it's going to round to 20. We just need to remember that this is going to be 2 sig figs. So you can write that out in scientific notation if you'd like. I'm just going to put a little mark there to remind myself that that's 2 sig figs for the end. Now if we compare these two numbers, just like we said in the beginning, we can see that Fg is greater than Ff. And because Fg is greater than Ff, put some newtons on here, this thing will accelerate. The system will accelerate. Now we can figure out exactly what rate the system will accelerate at. So what we need to do is get a net force. And the net force is going to be the difference between FG and FF. So the FF is going to oppose the forward motion, which is caused by this FG. So F net, our net force, equals FG minus FF. So F net equals 20 minus 7.4. So our F net is, and if we roll this back to 2 sig figs, F net is going to be 13 newtons. Now that we have the net force, we can actually solve for the acceleration of the system. And that's the key word here, is that it's the acceleration of the system. The whole system encompasses both boxes. So when we go to solve for the acceleration of the system, not only do we want to use the net force, but we need to use the mass of both blocks. So I'm going to set this up. We're going to use F equals ma one last time, where we have the net force and the total mass to plug in. So we're going to use 13 newtons for our force. We're going to use a mass of 7.0 kilograms, and we're going to divide these out, and we're going to get an acceleration of, with sig figs, 1.9 meters per second squared. So we can box that in. That is our final answer, and that's all this problem wants.